There's some more things I want to say about it.
Are you in PDOS?
Yes. That's going to be the next thing we talk about is projected or PDOS. Actually, no, we're going to do a population analysis thing because we need to understand that to get to PDOS. Densities of states, how do we define it? It was D what over D what? Yep. We can look at a band structure. We can note if there's a high number of states in a small energy window, what's going to happen to the DOS? Go up or down? Yep, go up. Okay. We drew the band structure yet again for a 1D hydrogen chain. Look like that. And then I put the densities, of states along this way. And which of the densities of states look like? Yep, even horns, and it should be symmetrical. At least, no, I'm going to mean more. Now, this is a chemist's way of drawing it. If you talk to a physicist and you show them this, they're going to get mad. They're going to be like, this is stupid. I don't understand why did you plot it this way? And there's good reason for it. Mathematically, what should our y-axis be? Like if we're plotting this as a y is equal to mx plus b, DOS should be our y-axis.
Because we have to integrate that. Should we get to what is being building?
Yep. And number of states is not the dependent variable, it's the independent variable. So physicists.
Oh, they plot it, yeah.
Uh-huh. You'll often see them plotting like this. So why do chemists do it this way? Lines up with the band structure. That's a good reason. I didn't even think about it that way. Yeah. Another reason. When you think about electronic states, what did you do for a molecule? What's our y-axis? Energy. And then like for H2, yeah. This feels more like an MO picture. So oftentimes you'll find chemists doing it this way. Material scientists, all over the map. Sometimes they do this, sometimes they do this. I'm even guilty of that. If I'm publishing in a more physicsy journal, I do this. If I'm trying to talk to physicists. If I'm trying to talk to chemists, I do this. When I go to physics conferences, all my DOS look like this. When I go to chemist conferences, all of them look like that.
Fortunately, it's just a matter of taking that.
Yep. Yeah. And in some cases, if I'm going to a weird conference like I went to in Amsterdam, it doesn't matter. They can look at both of them and have no problem with either of them. They understand the world we're in. Okay, so let's ask a couple of questions. So the first question. How does the DOS tell us about conductivity? Some people use metallicity and conductivity interchangeably. I'm trying to be a little more careful. I honestly see no problem with it, but some other people do. So what does the DOS tell us about conductivity? Right, it's all about the Fermi level. The higher the DOS at the Fermi level, what does that mean about conductivity? Yeah. And I'm going to put a statement generally. Why am I adding that statement generally? Yeah, there's always exceptions. Actually, Roald Hoffman says that chemistry is the science of exceptions, which I think is pretty fitting. I'm trying to cover my ass like a lawyer. That's the whole point. Yeah. What else can you do with the DOS?
You can determine. You all know what that says. You know what that says electrons, right?
Yeah, you do. I can tell you the number of electrons in the system. Yep.
Isn't that all probably then?
So if you integrate the DOS, what would I integrate up to get the number of electrons? Not quite. What's our D? Here, our integration parameter? Energy. So what would you integrate up to get the total number of electrons? Uh-huh. So HOMO in a molecule, what is it for a solid? Any special other energies we've talked about a lot? It is a Fermi energy. If you integrate up to the Fermi energy, it will tell you the total number of electrons. Based upon mathematical principles, like when you do calculations. Okay, what other stuff can it tell you?
So this is assuming that we're getting DOS from it, and we're not.
Probably more of a quantum chemical calculation.
Okay.
Experiment is a little different.
Because can you get DOS independently of band structure and everything, or do you need band structure?
You do not need, I have calculated DOS without band structures for molecular systems, but I don't know if they're as accurate as they would be with a band structure. My gut's telling me you need a band structure to get there, but I don't know that. I haven't thought about it that way. I'll get an answer for you. Yep. It can tell you the number of occupied states.
You do community, like community polls on
Maybe I will. I don't even know what that is.
you can post kind of small little paragraphs that you want us to see. Because your checks you're using I recommended the video, I don't have a choice.
Yeah, you must do what the algorithm says. The other thing is it can tell you a lot about bonding. When it's paired with other info. That's where we get something called the projected densities of states, PDOS. The crystal orbital overlap populations, COOP. And crystal orbital Hamilton populations. Which we're going to talk about each of those things later. Orbital populations. Crystal orbital overlap populations. Yep. Don't worry about what the acronyms mean right now. We're going to go through each of them. Or the other thing it will tell you is will your system distort? And that's where we run into something, chemists call it a Jahn-Teller distortion. Physicists call it a Peierls distortion.
Yeah, John Feller or John?
Jan.
John.
Okay. Now I want to talk about a molecular system, DOS. Now, Katie, erase this side. Because we're going to use some molecular examples later on. It'll help us understand these other weirdo things, what's going on. So next question, what does the DOS look like? For H2. Not really a periodic system that we're talking about. What would it look like? So we have to look at the electronic structure. If we have H2, what type of orbitals do we have? Yep, 1s, they overlap. What do we get out of it? Yep, and what else?
Sigma star goes 3.
Right. Okay, let's draw the densities of states here. Oh, I did. Thank you. For a molecular system, are these electronic states going to smear out at all? Are they gonna make bands? Are they gonna grow out? Not if it's molecular. They'll just say, yeah, it's gonna be a delta function basically. You're gonna get a stick. Boop. And then I should draw another one. Boop. Up here.
So even though it's unoccupied, it's still getting results.
Well, now where would we indicate the Fermi level in this system?
Would just be on the
Some people would elect to put it here. They would say right above there, that's the Fermi level. The spot I like to put it, go in there. Because that is the true definition, I feel. Whereas this is what you might get out of a calculation.
But isn't the calculation all that matters?
No, the interpretation of that calculation matters.
But the calculation is put there.
Because it's not necessarily true. What the computer program is doing is saying, where do the electrons run out? Here? Okay, I'm going to just put it there. It's sloppy programming. Because if it had to figure out, all right, I want to calculate the distance between an occupied and unoccupied, and then let's say you were suddenly looking at a metal where the densities of states does this, but you still have a Fermi level right here. They're touching, that's really, really small. Do computers handle infinity very well?
Oh,
No, you'd break it. So this is more, but if you put it into a molecular software package, so one that's designed for chemists, that would work out fine. But could it handle doing a large system that's periodic? No, it wouldn't be able to do it. Does that answer your question, Joe? Okay,
but I understood.
good. Any other